In this project, an attempt has been made to investigate the effect of the movement of a jet ski on the border of two fluids, water and air interface. Obtain the mesh file and the full training movie via this link. The geometry of this project is designed in ANSYS Design Modeler. ANSYS meshing software also has been used to create a computational grid and mesh for the geometry. Also, due to the sensitivity of changes in important components of the flow, such as velocity and pressure near the boundary of the two fluids, and also where the two phases collide with the body of the jet ski, we have tried to use finer and better grids and meshes. The mesh type used in this geometry is unstructured. ANSYS Fluent can model the effect of open channel flow, for example rivers, dams, and surface piercing structure in unbounded streams using the VOF formulation and the open channel boundary condition. These flows involve the existence of a free surface between the flowing fluid and fluid above it, generally the atmosphere. In such cases, the wave propagation and free surface behavior becomes important. Flow is generally governed by the forces of gravity and inertia. This feature is mostly applicable to marine applications and the analysis of flow through drainage systems. In the viscous model, the standard k-epsilon model has been used. That is a two-equation turbulence model that allows the determination of both a turbulent length and time scale by solving two separate transport equations. The standard k-epsilon model is in ANSYS Fluent falls within this class of models and has become the workhorse of practical engineering flow calculations in the time since it was proposed. Robustness, economy, and reasonable accuracy for a wide range of turbulence flows explain its popularity in industrial flow and heat transfer simulations. Also, it is a semi-empirical model. The standard k-epsilon model is a model based on model transport equations for the turbulence kinetic energy, K, and its dissipation rate, epsilon. The model transport equation for K is derived from the exact equation, while the model transport equation for epsilon was obtained using physical reasoning in the derivation of the k-epsilon model. The assumption is that the flow is fully turbulent and the effect of molecular viscosity are negligible. The standard k-epsilon model is therefore valid only for fully turbulent flows. The bottom boundary is a stationary wall with no slip. And here we should identify the zero against the volume fraction of the water as the secondary phase, that it shows that no water is allowed to enter from the up boundary condition. For setting under-relaxation factors, we should say that the pressure-based solver uses under-relaxation of equations to control the update of computed variables at each iteration. In ANSYS Fluent, the default under-relaxation parameters for all variables are set to values that are near optimal for the largest possible number of cases. These values are suitable for many problems, but for some particularly nonlinear problems, for example, some turbulent flows or high Rayleigh number natural convection problems, it is prudent to reduce the under-relaxation factors initially. It is good practice to begin calculation using the default under-relaxation factors. If the residuals continue to increase after the first 4 or 5 iterations, you should reduce the under-relaxation factors. Occasionally, you may make changes in the under-relaxation factors and resume your calculation, only to find that the residuals begin to increase. This often results from increasing the under-relaxation factors too much. A cautious approach is to save a data file before making any change to the under-relaxation factors and to give the solution algorithm a few iterations to adjust to the new parameters. Typically, an increase in the under-relaxation factors bring about a slight increase in the residuals, but these increases usually disappear as the solution progresses. If the residuals jumped by a few orders of magnitudes, you should consider halting the calculation and returning to the last good data file saved. Here is the air volume fraction two-dimensional contour. In this contour, you can see and check the velocity contour, that the maximum velocity almost is equal to 11 meters per second. The applied settings are recapitulated in these following tables as a review. Obtain the mesh file and the full training movie via this link. To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.